In this video, we're going to perform finite element analysis to calculate the shear strain on a cylindrical shaft that's been fixed to a wall and has 24 newton meters or a torque applied at the free end. To get started, let's do some calculations that give us a better idea of what we expect the finite element analysis to provide. So drawing this shaft connected to a wall, as you see here, we have given a diameter of 1 centimeters and 1 centimeter and a radius then of 0.5 centimeters. We have a length of 9.2 centimeters. We have a shear modulus given as 80 gigapascals, and we have a torque that's being applied with a magnitude of 24 newton meters at the free end. The torsion formula states that the shear stress, the maximum shear stress, is going to be given by the torque times the radius divided by the polar moment of area. And we can use a form of Hooke's law for this case of pure shear, where we have tau is equal to g gamma, and therefore gamma is going to be equal to Tc over Jg. Now the question is asking something interesting. It's asking about the maximum tensorial shear strain. And for that, you can go back and look at the notes where I discuss how the finite element analysis package that we're using, PrePoMax, has an interesting way of keeping track of the strains that are not normal. Okay, so that would be the shear strains. That's what we're dealing with here. And this is because when it does the tensorial math for things to work out, and we'll cover this a little bit when we get to more circle with plane strain, it's that that there have to be these 1/2 coefficients on the true shear strain in this tensor. Okay, that describes the overall state of strain for the system. So PrePoMax will give us these epsilon 1 1s, epsilon 1 2, epsilon 1 3, epsilon 2 3, epsilon 2 2, epsilon 3 2, and epsilon 3 3, and or did I already say that? But it will give these values to for us. But we need to recognize that the true strain is actually going to be essentially twice. Okay, so whatever we here will be twice what the true strain will be twice. These will be half. These values will be half of the true strain in the matrix. I realize I just made that kind of complicated. So when we look at our problem at hand, okay, the tensorial shear strain, say in the 1 3 direction, is going to be equal to 1/2 gamma. Okay, so when we want to plug in a value here for the maximum tensorial shear strain, we're going to multiply this quantity that we calculate by 1/2 to get it. Let's go ahead and pull up FreeCAD so that we can design out our, oops, that's the website for FreeCAD. That's not what we want. I just want the app. Here we go. And we're going to use FreeCAD just for the geometry, and then we'll go ahead and we'll perform the finite element analysis in the PrePoMax software. Okay, so to kind of get us going here, yeah, we can cancel this. We don't need that. We're going to create new, and we're going to go to the part workbench, and then we're going to create a cylinder. And the cylinder is supposed to have, whoa, that was wild. I don't know what just happened. Uh-oh. Uh-oh, uh-oh, uh-oh. Okay, well, let's just, well, okay, there we go. I'll have to flip back here. All right, so the cylinder is supposed to have a radius of 0.5 centimeters. It's supposed to have a length of 9.2 centimeters. Okay, so let's do that. So radius 0.5 centimeters and length of 9.2 centimeters. So radius 0.5 centimeters, that would be 5. millimeters, and the height will be 92 millimeters, like that. Okay. And we can kind of zoom out and take a look. Now, there are some interesting things that happen, at least with the latest version of PrePoMax that we're going to use. That's version 2.1.11. In previous videos, you may have seen that we transformed it to rotated it to bring it down. For some reason, I'm not quite sure what happens when you perform the transformation, but PrePoMax does not handle the axes perfectly well on the imported geometry. So we're just going to leave it in the vertical direction. We're going to be looking at things in the Z direction. Okay, we'll go ahead and we'll export. Okay, we'll select the object and then we'll export it. The unnamed cylinder, that sounds good. Okay, and then we will come over here. Let me bring over the downloads, and we'll come into PrePoMax, and we will open up PrePoMax. And we can close this and see that we have an opportunity to create a new model, and we will go ahead and import our geometry. Okay, where's downloads? Go, unnamed cylinder, and we will see that the length is not 9.2 centimeters, but is in fact something like 92 meters. So once again, we're going to transform and shrink our geometry by a factor of 1,000, like this. And it disappears. We can then click zoom to fit, like that. And if we move things around a little bit, okay, we see that, yeah, this is about, yep, it's about the 9.2 centimeters that we want, okay? Okay, so now we've got our geometry. Let's go ahead and start working on the mesh. I guess I can, well, I can do it either way. I'll create the mesh parameters here, and we're going to use this part. So we select that. Let's see how it does just with the defaults. We'll create the mesh. Ooh, that's not the greatest. Let's go back if we can, and we'll change the parameters. I want to make it a little more refined, so we'll do like 0.002 there, and that should make things a little better. And then we'll do the mesh. We'll create the mesh. Okay, that looks a little bit better. Okay, if I make it a little bit small, it's not. You know, I could do. I'll refrain from being a perfectionist here. All right, but yeah, okay. So then let's go ahead. Because we're gonna apply a concentrated moment at this end. Let's go ahead and define that surface there. So we're gonna create a surface. We're gonna select it, and we can just select that end just like that, and hit OK. For the reference point, we want to put that there as well. And we said that so it's the Z, okay, so this is going to be at 9.2 centimeters, okay, like that, and boom, it's right there, so it's perfect. We hit OK. The material, okay, we have to create an elastic material. What do we see here, though? We see that it's asking for a Young's modulus and a Poisson's ratio, so we need a Young's modulus and Poisson ratio. But do we have those? If we go back to what we saw here, we have a shear modulus of 80 gigapascals. They didn't give us an elastic modulus, or I didn't give you an elastic modulus and a Poisson's ratio. So let's examine a constitutive relationship that relates Poisson ratio, elastic modulus, and the shear modulus. And for many of the materials that we're dealing with, nu of 0.3 is not a bad value for, say, steel. And we can rearrange things to solve for the elastic modulus. So E would be equal to 2 times quantity 1 plus nu times G. So maybe this is a good time to, yeah, let's bring up the Colab. Let's go ahead and create a new script for us to use, or notebook if you like. We're going to import numpy as np, and we'll bring in a new cell. And let's see, we have G is equal to 80 gigapascal, so 80 E9. And we have described nu to be 0.3. And we're going to say, let's see, where is this stuff? Okay, G is equal to 2 times quantity of that thing. So G is, no, sorry, E is equal to 2 times quantity 1 plus nu times G. And so let's go ahead and solve. We'll say that or we'll go ahead and print. We'll do print E is equal to, what are you going to tell us? NP round of the E, and sure, we'll multiply by 1e to the minus 9, and we'll put in I don't know, a couple decimal places, probably overkill, and the units will be gigapascals, just like that. So what does it tell us? Okay, 208 gigapascals. That sounds like a reasonable value for steel. So let's go ahead and use this value in our PrePoMax. So over here, we'll put in 208 gigapascals, and we can put in 0.3 for the Poisson's ratio. All right, sections. Yes, we need to define one. We create, it's going to be a solid section, and we're just going to use the part. Click the part, click OK. Constraints. Yes, we're going to tie that reference point to the surface we created. So we're going to create a rigid body. Sorry, I used the word tie, but we're going to create a rigid body, okay, that is going to be connected to the surface and the reference point for us to apply torque. So we're going to do surface name for the section and surface one. So now we're using rigid body. I shouldn't have used the word tie. That's confusing. And now we can go ahead and bring in our appropriate physics. So that's going to be a static step. Now we can apply a boundary condition of a fixed wall here. And we hit OK. Good. That looks right. And we'll put in a load, we'll create it, and it will be a moment. And it's asking where is that going to be. We're going to select the reference point. Okay, and then the direction. Well, it's going to be in the z direction. Okay, and that will be applied that way. And what did we say? I think it was 24 Newton meters. Let's see here. Now we've got a few things running. So 24 Newton meters. And whoops, that's FreeCAD. Here's PrePoMax. 24 Newton meters, just like that. That's the magnitude. We hit OK. It looks like our problem is ready to go. And so let's do the analysis. Sure, go ahead and run. And it was very fast. We look at the results, and what do we see? Okay, we see some displacement calculations, we see some stress calculations, and we see the opportunity to put in some strain results. Now, before we click on some of these stresses and strains, let's go ahead and run some calculations that you could consider to be back of the envelope. So remember, we have equations that should give us the value for shear stress and should give us tensorial shear strain as well. So if we open up the same script, let's go ahead and expand on what we've been doing here. So let's put in our torque is 24 Newton meters. Let's put in our C, which is going to be 0.5 centimeters. Let's put in the shear modulus. Actually, the shear modulus is already there. Let's calculate out the J. That's going to be pi over 2 times C to the 4th. And that will give us units meters to the 4th. And let's calculate the shear stress, tau. So that will be T times C divided by J. And why don't we go ahead and print? Okay, cool. It put it out. So it puts it out in terms of, well, so there you can't trust the AI exactly. Let's go ahead and we'll spit it out in megapascals. Okay. And so for that, we need to multiply by 1 e to the minus 6. And other than that, it looks pretty good. Let's go ahead and calculate the pure, or not pure, the true shear. So we'll call gamma, okay, which is going to be, I could do it either way, but I can do tau divided by G. Okay. And we can, yeah, sure, if you want to print it now, that's fine. And I don't know, let's do it in micro strain. So we'll say micro strain, yeah. And we'll give it a bunch of decimals just in case. I'm actually not quite sure what value it's going to give us. Oops, I need to multiply by 6. 10 to 6, not 1 e to the minus 6. And then let's calculate the tensorial strain. So we'll call it the gamma divided by 2. Okay. Let's see, did it do it? Yeah, it got that one. I knew that. All right, good. So let's run this. We run it, okay, and so we see that we have a tau of 122 megapascals. All right, that doesn't seem to be, through the roof. And we've got values for gamma and for epsilon 1,3. All right, so this would be the tensorial shear strain. And we can see all these values, hopefully in PrePoMax if we did things correctly here, right? We've got kind of an opportunity to do the baby step, as I call it, in finite element, where you can do an analytical calculation and then see if your initial simulation gives you the same result. And then you know that you can be confident that at least your process is in place before you go into more complex calculations. All right, so we're looking for a shear stress of 122 megapascals. Let's think about that shear stress, okay? If maybe I should draw a little bit more. This is going to be lengthy, but I can draw on the fly. If this is the z direction coming out here, okay? I know this is awkward, everybody. All right. The shear stress is going to be coming. Oops, that's not very good. Let me just do this. Okay. I think it's better if I also define. Let's see, if that's z, that's coming out. All right, let's say that we have our x going upward. Okay, and we have x, so x cross y. Yeah, okay, so that would be this, like that. All right, that gives us the z coming out of the face. So we have x and y, and the shear stress is acting circumferentially around on the face. Remember, if you go back to our lecture, so what we would see is that here you have, a large shear stress that I can't keep track of, and then it gets smaller in a linear fashion as it gets closer. That one looks the same. I just want one good one. Okay, y like this. Okay, so it decreases linear. Remember, that's T rho over J essentially. So the maximum shear stress would be on the outer surface, and um, it's going to be maximum when it's along this x direction, okay, or on this x-axis, or on this y direction, as we see here, okay. And so what we need to do is we need to get to the outer surface, and we need to be looking at something that's on, let's say, the 3 face, the z face, in the y direction. Okay, that's kind of interesting, right? See how that shear stress is in the y direction? Or if we were here, it would be like when I say here at this point on the y-axis, the shear stress would be coming downward like this. Again, kind of crude. And so that would actually be in the x direction and on the 3 face. Okay, so if we're looking at, let's say, 1, 3, okay, so 1, 3, and 3, 1 are going to be the same. That means that we're looking at a shear stress or shear strain, okay, on the z face in the one direction. Okay, so let's take a look at the finite element and see how that plays out. Here, okay, you can see that there's a z direction, and so where we have this would be the z face, all right, or you have slices, and you're on z faces as you slice down, right? Slice, 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 slice along it. Okay, and we need to be on the outer surface. Well, that's good because that's available, readily available. And if we're looking for a maximum, okay, in the one direction, right, we found out that that would be happening on the y-axis. So like either here or on the other side, it's going to be negative if it's coming down on this side. So let's go ahead and look at stress 1, 3. And yes, it's saying that there's some type of maximum here. But if I line up things, all right, you see that maximum is actually, okay, on the negative y-axis, all right, coming out over there. So let's pick, I'm going to pick on this side something, all right, that I think is kind of y-ish, and maybe I'll go to a maybe a front view. Okay, so now we have a y direction, all right, and I need to pick a point. I'm going to just, it's pretty clear. I need to pick a point here on this axis that will give me an x stress, because we're on the one, we're looking at stress is 1, 3. So I'll query, and I'll pick here, let's say, and what do we get? We get that negative value we were talking about, okay, because this is on the positive y direction, and it says it's going to be minus 124 megapascals. What did we calculate out? In here, we calculated 122 megapascals. That's very close. That's within a couple percent. So that's exciting, just by pointing and clicking, right? And if I come down to this bottom here, all right, and I query a value, this is more or less, in the most negative y direction, okay, I get 121 megapascals. So we're very, very close to what we calculated for the shear stress. That's exciting. Okay, so now, okay, we've got our queried points, and we can kind of keep them and move on to calculating or looking at the values, the tensorial values for the strain. So we'll do an epsilon 1, 3. Okay, and everything changed. What do we see? We see that we have 754 microstrain, or 778 microstrain. All right, what did we calculate? We calculated out that we would have values of approximately, wait, whoops, wrong one, looking here, of 763 microstrain. All right, so we're within a percent, essentially, or close to within a couple percent of the actual values. And that's something to keep in mind. Both our analytical answers, like those that we're using just with the math, right, kind of represent representative ideal cases, and often with kind of average stresses and values in the problems that we're studying. And so it's unrealistic to believe that it's going to be exactly that value, right? Likewise, when we do finite element analysis, we are discretizing a perfectly round object with elements. And so it's also somewhat unreasonable to think that the finite element analysis will be absolutely accurate, especially because even if we get that geometry that is perfectly ideal, it doesn't capture what's happening with the non-ideal nature or the realistic nature of the problems that we're studying. But finite element analysis, once again, allows us to model very quickly complex geometries. Before modeling those complex geometries, though, you and I should perform a baby step to make sure that we can solve this analytical problem using a process in place for the finite element analysis. Before then, we change the geometry and use that same process to evaluate the stresses and strains in more complicated structures. Well, I hope you found this information, this video helpful. I guess I say for the sake of the assignment, what we're looking for is for one to essentially, take a screenshot of something like this, and then and you can, show the axes and everything and dimensions, and then, go ahead and paste that in to some type of file, and then upload that to Canvas. That's what we're looking for here. And of course, the values that you plug in the field for the tensorial shear strain should be kind of close to what you see here. Okay. Thank you for watching. I hope you found this useful.